Sorry, I feel a little bit out of place. As I am a condensed matter theorist, as you can say. Well, what's going on? Okay, this way. The other direction. On my is the other way around. Okay, I will tell you about elementary thoughts, because here you've heard in the morning about possible ways to do quantum dynamics and so on. And here, my purpose is much more practical. How to use it, how to, in a way, within the quantum mechanics which we have, how we can use it for the practical purposes. But of course, there will be some thoughts as well. Oh, it doesn't go that way. Okay, I know. Forward is the left or the right? The right. Yeah, okay. Oh, plan my talk is as follows. Actually, there is no Wojtek Żurek here. I posed a problem 2 years for him, whether the macroscopic wave function is more classical or more quantum. And then I just wanted to surprise him and provide some elementary thoughts on the problem which we are tackling. So I will say first elementary things. Oh, gosh, why does it go back? This is the slide. Yeah, okay. About wave function, then I will say a few things about macroscopic wave function on the example of Ginsberg-Landauer wave function for superconductor and Gross-Pitayevsky wave function for the condensed Bose-condensed system and its relation to the order parameter. Actually, macroscopic wave function is the order parameter, but then I will say a few words about the main thing, what we understand by decoherence in the system with broken symmetry on those two examples. That's how it is. And then practical implications. Okay, let's start from the beginning, from our grandfather. As we know, we have the de Broglie relations, which were generalization of Einstein relation for photons, but with energy we have frequency, and with the momentum we have the wavelength, or as we say in condensed matter, our wave vector rather than wavelength. And then, of course, you substitute this. That's the way how one could think. One can derive quote unquote wave equation. We have the relation for non-relativistic particles. Substitute that here. And then we have the so-called dispersion relation for a wave. And then you ask yourself, what would be the wave equation which for the waves, plane waves, would have this dispersion relation? And of course, then you arrive at that such equation, if you substitute plane wave here and here, you obtain exactly that. And of course, that was the easy way of deriving wave equation. And of course, then the principal thing due to Schrödinger was saying if this was the role of energy, this was the role of kinetic energy, so add potential, and then do the charge conservation number with the wave and with such a boundary condition, and you derive hydrogen atom, helium atom, and other systems. Okay, so that was how original one could think Schrödinger equation could have been invented in the simple way once you know the de Broglie relation. But let's now think a little bit about condensed matter. Does such thing exist in the condensed matter? And here I have the simplest possible example, which is harmonic oscillators, in which atoms are placed equidistantly, with certain inertial mass m periodically, and let's now induce vibrations. So we have some deformation at each lattice, nominal lattice sides, and make a classical equation of motion for such a harmonic chain. So we have, of course, the inertial term, which is second derivative of the, and then we have here force, which is the gradient of the potential. If you have harmonic chain, you have things like that. And believe it or not, and K dash the elastic constant because k is the wave vector. Believe it or not, Schrödinger, before he invented Schrödinger equation, found the most general solution of this equation, which is in the Bessel functions of the first kind. This omega 0 is the essentially resonant harmonic oscillator resonant frequency. 2 is because you have two neighbors, so therefore it doubles. And of course, and then he says, once you know for at t equals 0, once you know from the initial boundary conditions, once you know, determine this, you know that, and the solution is found explicitly. But in quantum mechanics, we address actually a different question. What would happen, because there you have, in this classical solution, one zeroed atom is distinct from all the other atoms because you start vibrating it, and then you have this quasi-oscillation propagating from this boundary point, from this initial point. But suppose that all atoms are indistinguishable. We really don't know which started first. We really don't know. If the neutron is just quantum particle, so even though the impinging neutron produces vibrations, but we don't know which atom it excited first. So then we have to change the solution into the form which makes explicitly the use of indistinguishability, because here just phase changes periodically, this is constant, so all sides participate in the same manner in the vibration, and since all of them are equivalent, we assume that this amplitude is 1 over square root of n, so mean square deviation will be multiplied by n, will be intensive quantity. But that's important is that we do that. Okay, then you substitute it to equation, and what you get, the omega versus k, this is the so-called dispersion relation now for elastic waves, and if k times lattice constant is small, so sinus is just x, and therefore you have linear dispersion relation. So therefore you have see here the role of velocity of light is played by the velocity of sound. Okay, and then of course you multiply it by h constant, and you can see that you have recover the de Broglie relation. But there you see here this equation, those waves have no Planck constant because h is here, and they are related linearly. In continuous medium approximation, this will be, you won't get that, this is for the lattice, but if a goes to 0, then you just get the linear dispersion relation. So lattice Planck constant does not appear, but they are classic waves. So then you can ask the opposite question. If for photons, for waves we introduce particles, for electrons we introduce waves. So now, what would be the corresponding particle for representing such a classic wave? And of course, you can derive the wave equation in the continuous medium approximation, and you can see beautifully you are getting some kind of Klein-Gordon equation. Okay, but then what would be the particles? So the fundamental question is, where is the associated with it particle? Now we will call it quasi-particle, because you have waves. You have no obvious particle, you have no obvious mass, because atoms vibrate like that, but the waves propagates along the chain. So it's something different from those individual vibrations. So it may have a different mass. Actually, it's a massless excitation in this. So then, we have reciprocal procedure, so we have to quantize now wave motion, which means we have to go to the second quantization. So by second quantization, we attach to waves, classical waves, proper particles in the quantum mechanical sense. And in what sense, I will say in a moment. So therefore, in the case of fermions, let's say with spin sigma, we attach field operator, we attach things which will be called field operator. With this displacement field, we'll have operator of displacement. So this is a field of operators numerated by to attach to each lattice site in the continuous medium approximation. But then, of course, in this new language, as you know, if you have psi bar psi, This is operator, particle number operator, particle number operator. So we deal, this is a real particle language because we have density of particles, operator, density of particles. And then, of course, if you use the variable number, occupation number representation of the Fock space, then this operator has acquires static or classical values. So you have really particle number, not probability, but particle number. So this language is closer to the Einstein interpretation of quantum mechanics, that the quantum mechanics should be understood in the sense, averages in the sense of ensembles like in statistical physics. Of course, there in quantum mechanics, it has been ruled out by Bohr, Bell, and other people. Here, probably because we have implicitly, we have immanently number of particles immersed when quantizing those waves, maybe this Einstein representation is correct. This is something worth saying more, but I won't be talking about that. And so that was from waves to particles in the second quantized sense. And of course, now we have field theory. Immediately statistics automatically must be built in. And as you know, there are two types of particles. One are bosons, and the others are fermions. As you can see, that they like to being collectively bosons. The more bosons jump into the states, the more they already are. And so probably Polish-speaking people will realize why I painted them in red. Okay, whereas fermions are individualists. So here are commune, and here is individual things, fermions. And what is so funny about Bose condensation of bosons? Particles do not interact. And this is the question I always ask students in undergraduate third-year course, Introduction to Condensed Math Physics. Why the system has phase transition? It's a phase transition, true, with singularities of physical properties, even though the system does not interact. The answer is because of statistics, because the fact that you have symmetric wave function already produces this correlation effect, which is sufficient to produce phase transition. And what is so funny about Bose condensation? The funny thing is that you have temperatures like that, let's say temperature equal to 5 steps, and still the kT thermal motion is much larger, much stronger than the distance between the levels. But still system condenses. Still there is macroscopic part, even though the thermal motion is larger than the difference between energies. Why doesn't it distribute like that? Most of them jump at certain temperature to the ground state. So there is something collective, intrinsic, where not only energetical factor, but the quantum mechanical factor, which drives it. And that this fact is phase coherence, that you have the thing, that you have small waves, small matter waves, and if the wavelength, thermal wavelength, the de Broglie thermal wavelength, which is proportional to 1 over square root of t, if it's larger than the distance between the which is density to minus 1/3 for three-dimensional system. If this is, here is temperature, here is just density. If this condition is met, then the system condenses. So in other words, its size of the de Broglie wavelength coincides with this average distance between the particles, classical distance between the particles, then the system condenses. And this is produced by the fact that from all those waves, you formulate they are in phase. The big matter wave, macroscopic wave, is being out of these partial waves is being constructed. So you have a stiffness of the phase stiffness, because if you could take gradient of the phase of those in phase animals, then it produces kinetic energy. Gradient of phase gives you velocity, so it produces kinetic energy, and therefore this is what is important. But let's try to do it a little bit more. So first of all, how do we do it? How do we describe such a condensation? Of course, we have total number, operator of total number of electrons. If the system is non-relativistic, then, of course, total number of electrons is conserved. So the particle number, total particle number operator is equal just to actual number of particles. And if you say, well, the particles are not localized in real space, but then in complementary space representation, momentum representation, momentum is a good quantum number. So I sum number of particles. And then what Einstein taught us, he said, there is a singular pipe, non-analytic singular distribution. When there is, we have to divide all those numbers of particles into the component at epsilon energy equals 0 and the rest. And this is a singular quantity, so therefore, this is non-integrable part when you try to integrate over, and then you can integrate only those excited states with non-zero momentum, which means non-zero kinetic energy. So therefore this is, and this is macroscopic occupied. But if macroscopic is occupied state, so this is classical value. All this is quantum, but this, then we say it's still also classical. Not only this, but also that. This singular part, and that's what we say. But that's not sufficient. That's not sufficient. This n0 is equal to n when t equals 0, but a non-zero temperature below this critical temperature, this is still macroscopic of the order of n, very rapidly grow from this critical point. But this is not sufficient. And then we go to the next step, which is Bogoliubov, which was taken by Bogoliubov. And Bogoliubov said, this is what Einstein was saying about Bose condensation is not sufficient. It's not complete in the sense that not only this n0 is a classical quantity, but if I take this sum, this a0, not only this is scalar quantity, but this is classical quantity. That the amplitude, that the creation operation itself and complex number. Of course, everybody recognizes that later it was regarded as the coherent states and so on, but that's essentially what it's saying, that the amplitude of this field is also a classical value, complex, but it's classical value, and this is in the Fock space. And this is not so trivial, as you will see in the moment. Of course, this A0 is not lattice constant, it's just the amplitude of operator A0. Okay, and this he calls, this is A0, this is ordered parameter. This non-zero, the system is condensed, partially condensed at least. If A0 is 0, the system is normal, just thermally, classically thermally distributed. And that was it was emergent type of approach. He did not derive it. He essentially assumed it. And this is what we mean by emergent features of the physical theory. Not everything can be explained by mathematics, at least if singularities and phase transitions. Something must be put by hand, and then we studied conditions under which such anomalous feature as that the operator is a number, it appears, it is stable thermodynamically, whatever. Okay, so then now I am ready to define macroscopic wave function. So macroscopic occupation makes it classical variable. Okay, this A0. So in second quantization allows for classical interpretation if n is large, because the phase transitions, as a rule, are defined in the dynamic limit. You can, for the purpose of this talk, you can essentially say that we have countable but infinite number of particles. And then field operator in the real space is a Fourier transform of this particle number operator in the K space. So we have K equals 0, it produces psi 0, and here for K on 0, you have Fourier component in real space, all the rest. And this we call macroscopic wave function, because of course it has just one variable, r, and but of course if you want to square wave function, then you have to have the wave equation. And of course Gross-Pitayevsky derived that equation. Is that this singular part of the occupation number is represented by the state which obeys nonlinear Schrödinger equation. Here is the interaction between between particles. G can be either positive or negative, and so on. But that's essentially a Schrödinger equation. But you can say, well, it's not strange if you have in the ground state number of particles. It's a pure state, so therefore you can write down the equation, the Schrödinger equation for them. But this is also for non-zero temperature. This preserve where you have this KBT, this thermal chaos, attacking this condensate all the time, and can't make it. And that's the reason why the equation is not so trivial. Okay, and the question about existence of this pure state, or at least the macro wave function, even at the non-zero. So now a little bit more before going to the fundamental part of my talk. Second example, BCS, Bardeen-Cooper-Schiffer superconductor. Order parameter is much complicated, but well complicated. Why? Because this is the so-called superconducting gap, and this is expectation value of the two creation operators. One of the state with the given momentum and spin up, the other with opposite momentum and spin down. So here you have set of quantum numbers, and here you have set of quantum numbers for the state reversed in time. So this you can understand that it's a creation of a whole. So essentially superconductivity tells you if you create electron, there is intimately connected within another partner with minus k, which we cannot neglect, what we would do in normal. But electron jumps from the Fermi sea, jumps and forgets the whole which is left is just independent of it. So this is very complicated, quite complicated for non-relativistic physicists, because non-relativistic model should conserve number of particles. And here, this is if you take Fock states with n particles. Here you have non-zero where you have n plus 1, n plus 2 particles. This will be non-zero. N will not. So therefore, you must have space, Fock variable number of particles. But fortunately, we know that there is so-called uncanonical ensemble in quantum statistical mechanics, so we can do with it. When average number of particles is assumed only preserved, not the actual number of particles, and the system works formally well. Okay, we have Fock space with variable number of particles with such such strange quantity as the order parameter. Why this? So then again, the same as you do in the case of bosons. So you Fourier transform it from this K space to the complementary R space, and this we call is what corresponds to the gap for given K states electron with given momentum. This is called order parameter, and this is called macroscopic wave function. Why? Because again, I can formulate wave equation. Now look, I haven't written here a time derivative, and this is a subtle point. I'll talk about that. Those B and A are known from the microscopic BCS theory, but instead of energy times psi, something like that, T minus critical temperature. But this of wave equation for all practical purposes. What is even important that the kinetic energy momentum has gauge invariance, is a gauge invariant quantity, and transform accordingly to with the vector potential according to that. And here I can tell you very interesting story. This equation which was written by Ginsberg in 1950, and this was told me directly by Ginsberg. 1950, Ginsberg left Moscow, and the proofs came to Landau, who was supposed to do the corrections. And they asked, the editor asked, what is the E star? And here M star should be, I forgot to put M star. What is this E star of those objects? Cooper pairs were not known then as yet. What is this E star and M star? And Landau has written, this was, as Ginsberg put it, this was the only sentence which he put into the paper. And he wrote that there is no physical reason to assume that it's not just charge of electron and the mass of individual electron. And of course, it was wrong, because this is mass in this equation of 2 electrons and the charge of 2 electrons. But, you know, the geniuses, if they make mistake, they are right. So if you calculate, for example, penetration depth, the E star and M star appear in such a combination that the result is correct. And they were comparing that with experiments, so they are getting right answer. So you can be wrong, but still implication holds. So you have this sort of order parameters, or actually this one, and you have the corresponding wave equation. And now you ask, to what extent is a quantum object, this psi, and to what extent is classical object? And for all practical purposes, this is a quantum object, even though, as you can see, this thing here is an average. So therefore, this is an average quantity. Well, true Fourier transform of the scalar quantity. So this is in a way, it's like an ordinary wave function. Well, maybe complex, but ordinary, but still has all quantization rules. I mean, quantum Josephson effect, and so on. And so therefore, for practical purposes, it's quantum. So therefore, you can say that the breakdowns of symmetry, breaking down of symmetry, preserves quantum nature of macroscopic effects, not just decohere them, not makes them just classical like classical particles, which we heard here a few times, but it can preserve some principal features of quantum objects. So, and you can study, there are hundreds, if not thousands of papers on psi of R, and everything has been measured compared with experiment, as you know, in superconductivity, you can even measure phase, at least phase changes, via the Josephson effects. So there is not this arbitrariness, at least not to the extent in the Born interpretation. Here, of course, there is a constant phase factor always, but differences of phases depending on the changing physical condition by applying magnetic field and so on, all this can be measured very beautifully in Josephson effects. But I, of course, don't have time to talk about that. How much time have I got? 15 minutes. So 5 minutes would do. Okay, now decoherence. Now decoherence. How to go to classical through decoherence. If those averages are still quantum, so can we do decohere the system into the true classical sense? Okay, so as you know, here the system is, in infinite condensed matter, the spectrum of excitation is continuous. So smallest thermal motion, chaos, can disturb the system. So therefore, you can say that maybe our scale of energies, and this can change continuously, because excited states are very close to the ground state, if not single particle, because there is a gap, then collective excitation have no gap. So therefore, you can say this is KBT. This is the accuracy. So therefore, the time for to decohere, at least thermally, it's something like that. So this is something like that. And this means if you have system at 1 Kelvin, or God forbid at 10 Kelvin, the system lives for something like nanoseconds or tens of nanoseconds. And this is not good, making quantum bits, qubits from superconductor, because it will decohere, information will be lost in nanoseconds or in picoseconds. But fortunately, there is. And I have learned lately, and that's the answer to my partner, Wojtek Żurek, estimate broken symmetry for n-particle state. And it's absolutely wonderful if you have broken symmetry state. Time for spontaneous decoherence is what is here written, but of course this 2 pi is what h was taken instead of h bar by number of degrees of freedom. So you have, if you have 10 to 24 particles, this immediately becomes something like 10 million years. So therefore it doesn't decohere for a long time, so you calculate as long as you can, unless, but of course economists will not let you to use computer for such a long time. It will ask you to change it 10 times in the meantime, if not 100 times. So therefore, why this n factor? Because if you have broken symmetry, I will explain on the example of spins. Suppose you have ferromagnetic order. Suppose you have, so you have n spins, which is what is broken symmetry state is out of those spins. The theory tells you Hamiltonian voltage can be like that, can be like that, can be like that, can be like that. The only thing is that they are aligned. But to change such state into another broken symmetry state, let's say these are Ising spins, so they can only have up or down. You have to turn 10 to 24 spins, because you have to change one macrostate into another macrostate. Here you have to break this phase stiffness for those 10 to 24 spins, and that then costs astronomical amount of energy, and that's why the system lives for so long. And there you have then, but of course, this is 24. But then computers are not made of moles of particles. They are made of 10 atoms, 100 atoms, 100,000 atoms. And if you have, for example, 10 to 5th particles, 10 to 5th, then it's something like 10 minus 6 seconds. So back again, even though you have a broken symmetry state, you are not doing so well. But of course, there is another problem, which here appears, which is as following. If the system is finite, has only 100,000 particles, then does it have a broken symmetry state? Can it have? Even though, because really to have infinite response, to have these singularities, this stiffness, infinite energy, you need practically infinite number of particles. Infinite number of particles. That's the principal question. And then you now see why nanophysics in this quantum electronics. Because we have this small system of this 1,000 of electrons, let's say, of spins, attached to electrodes, which have broken symmetry state. And in a way, you do operation on this small nanoscopic system, but it uses the stiffness of this broken symmetry state of the whole macroscopic system. And that's the one of the principal, fundamental meaning of the nanophysics these days, used in quantum electronics. Of course, here I put at the end, there are the earlier criteria were those overall Landauer, and he said that the energy and the energy uncertainty is T times the change of entropy, change of thermal energy, and since reversing the spins is log 2, entropy is log KB log 2, so therefore the criterion, Landauer criterion, is similar as I have written for independent particles, but only this logarithm 2, but this is something like 0.693, so therefore this doesn't change much. So therefore, whether decoherence, thermal decoherence, understood roughly as I put on the slide before, or whether understood in thermodynamic sense, doesn't save us. What can save us only is the stiffening, essentially a stiffening system, so that the individual thermal chaotic jumps do not play that important role. Or, of course, also change the temperature. For example, quantum, as you know, D-wave computer is immersed in this ultra-low temperature equipment in Alamos. Question, of course, can this small system exhibit state with broken symmetry? This is the question. And quantum dots coupled to electrons with broken symmetry, and what I think I have said why with this pure quantum type of questions are related to nanophysics or nanotechnology. So conclusions, whereas the wave-particle duality works well as far as the energy excitation spectrum is concerned, does not provide any clue about the particle localization, because you can use either position representation, momentum representation, and so on, but we really want to do particle, we want to do operation in particular, quantum mechanical or quantum electronical operation, we must localize it. What to do then? First, start with the proper particle language, second quantization, and consider many particle states. Then the decoherence problem is not so acute if you involve broken symmetry state. So incorporation, so therefore the only practical remarks we have, incorporation of some condensed matter aspect is required to construct reliable operational and small quantum devices such as quantum processors. This is with question mark. Okay, and that's it. Thank you.
Maybe I have a question. So an ordinary, usually a single, like a Schrödinger wave function for a single particle is really a non-relativistic limit of a Klein-Gordon field.
Yes.
So if you take your composite particle,
yes.
And you can view it, you could view it as a limit of a Klein-Gordon field, if you like, I suppose. But
not exactly.
That was my question. How you would
no, because you see, Klein-Gordon equation or Schrödinger equation or Dirac equation is for single particle. Here you have effective equation, and the environment is encoded with nonlinearity or renormalization of this energy, and on because it's nonlinear, therefore it's a completely different class of solution. Different, not Bohr, you can say, not Bohr radius appears, but coherence length appears, which is immersed in the interactions. So it's the same language, but a completely same scheme, but completely different way of interpreting the system.
Okay, thank you. Right, if there are no more questions, let's thank the speaker again.
Thank you.